years of combined industrial and academic experience. His areas of research include multifunctional and smart composite structures, multi-scale modeling, and variational asymptotic method.
Sir, I object the word former. I am still an NMCADet.
Yeah, once an NMCADet, always an NMCADet. Our umbilical cords are long and strong.
You can take out the person from ISC, but you cannot take out the ISC from the person.
Absolutely, absolutely.
So, sir, Anup is with me.
Okay.
So I will be showing the first a few things, and then Anup will take over. So
Sure.
is my slide visible?
Not yet. Looks like you have taken some of the dogs from our campus.
Which one is shared then?
And now we can see it. Yeah, yeah.
Okay.
We were seeing it just a minute back.
Presentation.
We see it.
Yeah. I think now it is okay.
Yeah.
Okay. Okay, sir, ma'am and audience, it is a privilege to be back to ISC, of course, in virtual mode. So along with me, Anup is there. So he is actually working on this asymptotically accurate equivalent single layer plate theory. So what happened, I joined IIT Ropar a long time back, and since we are a new institute, we got a lot of young people who started collaborating. So overall, I am heading this Muse lab over here, and this audience doesn't need the introduction of VAM. But what we did is that we tried to apply into various domains, sorry. So for anisotropic and inhomogeneity, so basically the core idea is that if you take broader categories of material like composites, which are inhomogeneous at different stages through the thickness, and functionally degraded material which are isotropic, they are treated as isotropic or orthotropic, but they have a continuous smooth variation. So what we wanted to understand is that if you treat them as that type of mathematical function, what is going to happen. And recently we have obtained very good results in functionally graded material, where we were able to give the closed form analytical solution in a for transverse shear component. In fact, the paper got accepted just Saturday only, and I pinged sir that, sir, after a long time we have been able to crack it. Now with that, we have been pursuing a lot of things, and since we understand that closed form analytical formulation is not always possible for all scenarios, so for practical implementation, that you will see that we have migrated, or we have channelized into many of the domains like this bulletproofing, so impact analysis for multi-layer structures, which is metal, ceramic, and composite in between. For extension, twisting, bending, coupling, of course, this is extension of the work of NMCAD. And now recently we have this shear lag problem. Also, we have been able to formulate a analysis strategy where we can analyze n layer of shear lag issues in continuous fiber reinforced composite. Both these analytical and numerical actually gets into application into few domains. So as you can see, the center one is actually right now we have been very much involved in the type 4 composite cylinder modeling for automobile application, particularly right now. And in between, there are few collaboration which led to the functionally graded or the tuned manipulator. So the last one that you are looking, actually this is a curved manipulator, which is derived through the curvilinear beam theory. So the development is mostly numerical, was done by the student, and then he optimized the structure. So you will see that the structures are actually, there are holes, there are some mass distribution has taken place. And further, of course, to this presentation, we have the stiffened structures. And in stiffened structures, basically what happened, we have the stiffener, the locations that we observed that For symmetric stiffeners, the analysis is actually pretty straightforward, but stiffener in which you have a, asymmetry or stiffener is in one side, in those cases we wanted to understand how they will behave, and for that we started from a very basic understanding that how these stiffened structures can be analyzed from basic plate theory, and can we give a better insight using variational asymptotic method. And this is where Anup's work comes into picture. So he has started with basic analysis of Stiffened structure using the non-stiffened structures, the plate analysis. Then he has extended it to symmetric stiffeners, and you will observe in the presentation that for symmetric stiffeners also the results are pretty good. The asymmetric stiffness that we are discussing, that work is Anup still doing, and your suggestions and input will be very much helpful in this regard. So with this, I will give the con to Anup, and he will carry it forward. Thank you.
Hello, am I audible?
Yes, Anup, you are.
Yeah.
Maybe you can turn the webcam slightly more towards your face.
Yeah, okay.
Center your face on it. Perfect.
Is this perfect? Okay.
Yeah.
Okay. Thank you for giving me this opportunity. So my work is basically on the development of a BAM-based equivalent single layer plate theory, and I have implemented this plate theory for the analysis of the stiffened structures. So here is the summary of the work that I have done. So plates are working. No. Yeah. Yeah, so plates are basically three-dimensional structures. So we can use three-dimensional elasticity to analyze these structures. But the problem with the three-dimensional elasticity is that that it requires too much computational cost, and in many cases the analysis becomes too difficult that we cannot solve it by the three-dimensional elasticity approach. So that is why we go for dimension reduction. So for the dimension reduction, there are basically two approaches. The first approach is in the first approach we use variational asymptotic method. So variational asymptotic method gradually reduces the dimension of the structure in a mathematical rigorous manner. So it takes the advantage of the smallness of one dimension as compared to other two dimensions, and this method do not require any assumption a priori, while in the second approach we make some assumptions. So in these assumptions we establish a relation between the primary variables associated with the whole domain of the plate in terms of the primary variables associated with the reference plane of the plate. So the present model, in the present approach, I have created a plate model by a kind of fusion between these two theories. So in the present theory, we have developed a asymptotically correct plate model. So this model contains higher order derivatives of generalized strains. So to get rid of these higher order derivatives, we have considered a axiomatic or presupposition based plate theory. So we have imposed a condition between these two theories, that these two theories are isoenergetic. That is, they absorb the same amount of energy for the same deformation pattern of the reference plane. So considering this condition, we find out the expression for the transverse shear force resultants Q1 and Q2, and we use these transverse shear force resultants to eliminate the higher order derivatives of the generalized strains, as a consequence of which we get a modified asymptotically correct equivalent single layer plate theory. So here is the kinematic formulation. So here we have a reference plane of the undeformed plate structure, and after deformation it goes like this, shown in purple color. And here we are considering a point B on the undeformed structure BS. So after deformation, this point goes here, B prime, BS prime. So this position, the point B assumes this position if we rely on the well-known Kirchhoff assumptions. But if the Kirchhoff assumptions are not valid, so the actual position of point B may differ. So let the actual position of point B is here. So the difference, the vector joining these 2 points is the warping vector. So our objective here is to find out this warping vector. So to find out this warping vector, we find out the position vector associated with the deformed structure and the undeformed structure. So having these position vectors, we can find out deformation gradient tensor, and with the help of this, we can find out the linear strain tensor. So the linear strain tensor comes in this form. And here we are considering monoclinic materials. So the stiffness matrix for the monoclinic materials is shown here. Now we want to find out these warping components W1, W2, and W3. So to find these out, we have used principle of virtual displacement. So here is the displacement statement for this virtual displacement principle. So this statement gives Euler equations and associated boundary conditions. But the problem is that the Euler equation that we get using this equation are too much complex, and actually they involve coupled PDEs. So we cannot solve them by the analytical methods we have. So in this case, the WAM comes into picture. So what we do, we apply WAM. So in WAM approach, we first arrange all the terms of this statement as per their order of significance. And in the first perturbation, we take the most significant portion of this statement. And we find out the corresponding Euler equations and boundary conditions. So we solve these Euler equations considering the boundary conditions and get a warping vector W. But this warping vector W is not complete as we are not taking the full energy into account. So what we do, we go for the next perturbation. So in the next perturbation, we include some more higher order terms in our analysis, and we again find out the Euler equations and boundary conditions, and we after solving these Euler equations, we get more accurate expression for the warping vector. So we keep on moving in like this, perturbing like this until we get sufficiently accurate expression for warping vector W. So here in this approach, we have gone up to the second perturbation, and after second perturbation, I have got the warping vector W, and substituting this warping vector W in strains, we get strains in this form. So here now the difference that our plate model has, that we are trying to find out to get rid of here the G kappa, H kappa, and N kappa are derivatives of generalized strains, higher order derivatives. So we want to get rid of these higher order derivatives. So here is the main difference in the present model. So to find out to get rid of these terms, we have used equilibrium of forces in the transfer direction to get these two equations, where Q1 and Q2 are the transverse shear force transverse shear force resultants. So now these two equations can be rearranged in this form. So now if somehow we can manage to find out Q1 and Q2, then we can substitute these Q1 and Q2 here to get these expression for these two quantities, and then we can substitute these two quantities here in these strains to get rid of the higher order derivatives of the strains that causes problem in the analysis. So to find out these quantities, I have considered a presupposition based place theory like FSDT. So in FSDT, we have expression for Q1 and Q2 as shown here. So here K1 and K2 are shear correction factors. So we want to find out these two shear correction factors. So to find these out, we have imposed the condition that this FSDT model and the WAM based model are isoenergetic. So imposing this condition, we find out values for of K1 and K2. So we substitute K1 and K2 here in these two expression, and then we substitute Q1 and Q2 here, and finally we substitute these two expressions here to find out to eliminate the higher order derivatives. So final expression for the strains we get in this form as shown here. Now the problem reduces to find out these uh, the primary variables like u1, u2, u3, phi1 and phi2. So to find out, to determine these quantities, we have again used principle of virtual displacement. So here in this case, we are taking u1, u2, u3, phi1 and phi2 as primary variables. So here is the virtual displacement statement. So this statement is in deformed configuration of the structure. So we change the domain from deformed configuration to undeformed configuration. So after some mathematical manipulation, we get this expression. So here expression for capital gamma is shown here in this slide. So this is the final expression for the strains for the plate model that we have developed. So we have used this model for different applications. So here is first we are going to validate this model numerically. So here is the plate. Here we are considering a plate, an example in which we are considering a square plate. So this square, the geometrical details of this plate are given shown here, and we are all the four edges of this plate are simply supported, and we are applying a sinusoidal force on the plate, and we are considering a orthotropic material. And for the comparison of results, we are considering these non-dimensionalized quantities. So here is the comparison of the results with the result that we get from CRPT and FSDT and 3D FEA approach. So here we can see that the I'm sorry for the disturbance. Oh, so here we can see that we are getting improved result as the A over H ratio is increasing. So this is because while ordering of the different terms of the in WAM approach, while we ordered different terms of the virtual displacement, so we consider the A over H ratio. So that is why the results are getting improved when we are taking A over H larger. So here we can also observe that our results, our present approach is giving better results for the displacements and for the shear stresses. And however, it requires, so the results are better than the FSDT plate model. However, it requires the same computational cost as the FSDT2. And here is the comparison of the shear transfer shear stresses. So we can see the improvement in the transfer shear stresses over the FSDT. Now we have considered a second example. In this example, we are considering a 4-layered cross ply. So here this is a rectangular plate. So B is 3 times more than A, and we are taking all the 4 edges simply supported, and all the conditions are same that they were there in the first example, and we are considering the same non-dimensionalized quantities. So here is the result in tabular form. So here also we can observe the significant improvement in the the displacement and the shear stresses over the FHDT. So here is the same thing. We are getting better result for increasing A over H. So here is the comparison of transfer shear stresses. So we can see the improvement over FHDT here also. Now to look at how does the present theory behaves when we are changing the anisotropy of the material. We have done this study. So in this study, we are changing the anisotropy of the material by changing E1 or an E2 ratio, and we are seeing how the normalized displacement is changing as we are changing the E1 over E2 ratio. So here we can also observe that the present theory is giving better result than the CLPT and FHDT do. So now we have used the present plate model for the analysis of the stiffened structure. So to analyze the stiffened structure using the present model, we are, instead of considering a stiffened plate structure as a combination of two structures, a plate and stiffener, we are treating the stiffened structure as a one single structure with varying thickness. And we are using the present plate model to reduce the dimension of the structure. So we take the mid plane of the structure as reference plane, and we reduce the dimension of the structure using the present approach. And we finally get two-dimensional model for the stiffened structure. So using this approach, I have attempted a numerical example that is shown here. So in this example, the geometrical details of this example are shown here. So we are considering a cross stiffener, and we are considering homogeneous material. The boundary conditions are shown here. So here is the results. So here we can see that the results are in very good agreement with the literature. So here the reference one is a paper given by Reddy. Now, since this present approach is working good in the symmetric type of stiffeners, but symmetric type of stiffeners are of a practical little use. So we are trying to extend our work to analyze the unsymmetric type of stiffened panels. So here we are considering two approaches. In the first approach, we are shifting the reference plane to somewhere else than the mid plane of the plate. In this approach, in the present model, we have shifted the reference plane to the plane of the plate where the stiffener is attached to, and we have used the present plate model to reduce the dimension of the structure. And after reducing the dimension, we are left with a two-dimensional plate model, and we analyze this two-dimensional plate model using a FEM code created by us, developed by us. So in the second approach, instead of shifting the whole reference plane, we are taking a localized shifting in the reference plane. So we shift the reference plane. So here is the localized shifting of the reference plane, and the present plate model is used to reduce the dimension of the structure. So also in this for this type of approach, we have developed a finite element code to analyze structures. So here is one example that I have solved using the second approach, where we are considering localized shifting in the reference plane. So here are the geometrical details of the details of the plate that we have studied using this approach. So here are the results. So first, so here we have done the convergent study of the analysis that we are doing using the developed code. So we can see that the results are converging very rapidly, fast, and we can compare the result, the center reflection of the plate with the result available in the literature. So we can see that there is a very good agreement in the result that we have obtained using the present approach. Also, I have compared the displacement of the plate along the central line of the structure. So here is the plot for this analysis. So here we also I have compared these results with the result available in the literature. So here we can see that the present approach is giving very good agreement, is in very good agreement with the result present in the literature. So this model, the present plate model, can also be easily used for the analysis of the buckling of plates. So we can find out the governing differential equation for the buckling of plates, and we can then use we can assume a displacement field to solve these equation, or we can go for numerical solution, like we can use FEA. So here is the work that we have done. So here is, so conclusively we can say that the present plate model is better, gives better results than the FSDT plate model do, but it and however it requires the same computational cost. Also in the present model, we do not require any shear correction factor, and this model, the present model, can be used for the analysis of the plate type of structure in a fast and efficient way. Also, this type of plate model can be used when there is a variation in the thickness dimensions, variation in the structure in the thickness direction. So this is all that we have done. So here are the references. Yes, sir.
Thank you very much for your presentation,
Yes,
Anup. It was really good. Congratulations also on your recently accepted Journal of Applied Mechanics paper.
Thank you, sir.
For a long time, I already told your advisor, Professor Padhee, for a long time, this particular problem, at least the closed form analytical solution, was thought impossible. So
yeah,
it's a real good breakthrough in the field. So I'm really happy that my academic grandson has done it.
we are also very much excited that we have got the paper got selected in without any review. So we are
right.
So,
so your advisor, of course, he'll take issue if I tell when he was here. So he's still here, according to him. One of his Journal of Applied Mechanics paper was on radial deformation when a circular cylinder is subjected to torsion. And that was also something which was really strange for a lot of people. So it's nice that Journal of Applied Mechanics accepts these kinds of papers which are sound controversial, right in the title, but eventually are a good breakthrough in the field. Can you go to your slide number 10?
Slide number 10, yes, of course. Here. Yes, sir.
Yeah, 9 maybe, sorry.
9, okay, sir.
Yeah.
This one.
Yeah, so the strain has only 5 terms. So is there something that you're minimizing with respect to that to remove dependence of
actually,
energy?
we are considering here strains having 6 terms here. Okay, so what I did for when we consider strains correct up to H over L order. So here we are considering strains correct up to H over L order. So when we consider, we go for this much accuracy for strains, then we can prove mathematically that in this case the transverse strains sigma 3 becomes 0. Transverse stress sigma 3 becomes 0.
Right.
So in this, so that is why we can apply plane stress condition. So that is why I have used plane stress condition here.
Okay. And while you stay on this slide 8, this K1 equal to K2 equal to 5/6 was an assumption that Timoshenko had made, but this is something that you are deriving from the asymptotical theory, right?
Yes, sir.
Yeah. So that's also a very important result for our communities. Right? So I think these aspects need to be highlighted whenever you present, because it could tend to get overlooked, some of these very important findings. Because once you have this particular model in place, you could probably look at various other kinds of Timoshenko applications where it was empirically assumed these shear correction factors. Now you probably will be able to get for certain, at least certain regular geometric shapes, the actual asymptotically correct values of these shear correction, so-called shear correction factors, which of course, if we use your theory, we won't even need those correction factors.
Yes, sir.
Yeah.
Yes, sir.
And also, I like this approach of the isoenergetic, where you're trying to actually equalize, because somewhat similar thing has been done by Wenbin Yu by minimizing the error between the.
Yes, yes, sir. So that approach,
right. So
yes, so becomes involved complicacy. Okay, so
right. Absolutely, absolutely.
Yeah. So here,
right. This is a much more straightforward
and that
because
that
our
approach.
Whole, go ahead.
Yeah. So in that approach, we find it difficult to implement when the properties or the structure is changing in the thickness direction, because in the when you approach, we have to do through the thickness analysis for each of the structure. So when the through the thickness analysis is changing at when we are moving along the reference plane, so that approach becomes very difficult to implement on. So, but in the present approach, we can implement it when this is happening.
Right. So one is in terms of the advantages you get over implementation. The other is also in terms of the very philosophy involved, because right from Berdichevsky, Professor Hodges, and the entire community that is associated with VAM, we have taken dignity in the fact that we have minimized the ad hoc assumptions, if not completely eliminating it. So I think from that perspective also, there's no point when you have an asymptotically correct theory, you're trying to get something which is trying to curve it into a Timoshenko model for beams, or let's say a Reisner-Mindlin kind of a model for plates or shells. It's kind of working around to touch your nose all the way instead of touching it directly. So I think these are all huge advantages. I'm sure I have not had a chance to read your paper because it's still, I think, in press. But though you might have highlighted these when you present it at conferences or when you get a chance for your career interviews and things like that, I think these are the things that you have to kind of highlight and bring out more, so that people kind of tend to appreciate what is your major contribution or value addition to this field.
Yes, sir. Okay, sir. So thank you. Are there any more questions from the audience? Or okay,
there was a slide where you show two representation of the stiffness panel, one with a continuous midplane and one with a midplane that got changing under the stiffeners. I think
stiffness, probably you are talking about this slide.
Yeah, this one. So I do not understand in that one that you change the midplane. How can you do the continuity from the two midplane?
Yeah.
Or you do not know?
Yeah, continuity is actually issue. So that is why we are considering this. We are considering different alternatives for this approach. So here, actually, what I have done in this approach, we have to maintain the continuity. We have shifted the stiffener so that these two reference planes becomes coplanar. But this approach is still under review. So we are working on this approach. However, this approach is yielding very good results, but still we have to find out a sound proof for all this. Okay, sir. Okay, thank
You You
you.
have to be very careful about the continuity over there. But also the other thing is in terms of these stiffeners, of course, it's a very, just to demonstrate your case, you've taken a very simple case of the cross-section geometry of the stringer.
Yeah.
But
Yeah.
I think the typical hat stiffeners or many other combinations like the Z stringer,
Yeah.
etc.
Yeah.
For those, you have to probably think about what are the kind of approaches that you have when you have a part of it not in contact with the plate, but bending and having a different geometry. So have you given any thoughts towards that?
No, no, sir. Up to this point, we haven't done this. All this. Okay. Okay. Thank you for your.
Anybody else?
Okay.